Good day everyone and welcome. Today, we delve into the fascinating world of scientific language models with our presentation titled Galactica, a large language model for science. This groundbreaking research explores how language models can revolutionize the way we access, organize, and reason with scientific knowledge. Stay tuned as we uncover the potential of these models to disrupt traditional paradigms and provide a new interface for knowledge. Let's embark on this scientific journey together. Our research delves into the potential of language models to disrupt the traditional store and retrieve paradigm. We're exploring how these models can overcome the limitations in reasoning and organizing information that have been a bottleneck for knowledge throughput. We've found that language models are incredibly adept at absorbing technical knowledge. They can understand complex LaTeX equations and chemical reactions, and their capabilities scale smoothly with model size. This absorption power could give language models a significant edge over existing retrieval pipelines, as we've demonstrated in citation prediction tasks. In essence, we're opening up a new frontier where language models could become a valuable tool for exploring scientific literature and knowledge. We've identified a key issue with current models. They lack the architectural change necessary to support adaptive computation. This limitation hinders their ability to perform tasks in a human-like manner. To address this, we've proposed a novel method. We've introduced the use of a working memory token approach, which has shown significant improvement on mathematical MMLU and math benchmarks. Furthermore, we've explored the potential of language models to act as a bridge between scientific modalities and natural language. This opens up exciting new avenues for the application of these models in various scientific fields. The traditional approach to accessing scientific knowledge has been a store and retrieve paradigm. However, this method has its limitations. It heavily relies on human effort for reasoning and organizing information, which can lead to a bottleneck in knowledge throughput. This is where our research comes in. We aim to disrupt this paradigm and introduce a new way for humanity to interface with knowledge. The figure here illustrates the concept of model-machine symbiosis, a key idea in our work. This concept represents a shift from the traditional paradigm, aiming to alleviate the burden on human effort and increase the efficiency of knowledge processing. Language models have shown immense potential in absorbing and utilizing scientific knowledge. They are poised to disrupt the traditional paradigm, providing a new interface for accessing knowledge. However, current language models face a significant challenge. They lack an architectural change that supports adaptive computation, which limits their ability to perform tasks like. To address this, we propose a method that uses a working memory token approach to improve performance. This approach suggests using language models as a bridge between scientific modalities and natural language. This could potentially revolutionize how we interact with and utilize scientific knowledge. In our research, we've utilized datasets such as PubChem Compound, UniProt, and RefSec Genome. These have been instrumental in our work, especially when combined with data augmentation techniques, which have significantly enhanced our model's learning capabilities. Looking ahead, we see great potential in expanding the number and size of datasets that bridge natural language and natural sequences. This approach is likely to further boost our model's performance. Additionally, we're considering relaxing constraints on the size of the corpus we use in future work. This could open up new possibilities for our model to learn more effectively in a multimodal setting. Our research proposes a novel approach to scientific knowledge absorption using language models. This involves a unique working memory token approach and a method to bridge scientific modalities with natural language. The working memory token approach has shown promising results. It has significantly improved performance on mathematical MMLU and math benchmarks. This approach allows the language model to compose a curated knowledge base, which is particularly useful for knowledge-intensive question-answering tasks. The results have been impressive, with our method outperforming existing ones. In essence, we're leveraging the power of language models to transform the way we access and process scientific knowledge. This could potentially disrupt the traditional store and retrieve paradigm, paving the way for a more efficient and effective interface for humanity to interact with knowledge. Our research has shown that language models can serve as a bridge between scientific modalities and natural language. For instance, they can learn tasks such as IUPAC, naming through self-supervision. Furthermore, it's possible to formulate complex drug discovery tasks, like MoleculeNet, in a natural language prompt. In terms of data, we've utilized datasets like PubChem Compound, UniProt, and RefSec Genome. To enhance the learning process, we've applied data augmentation techniques such as order randomization and format randomization. Importantly, we've only taken a small subset of entities from these datasets. This approach ensures that the model doesn't become overly biased towards learning natural sequences over natural language. This balance is crucial for the model to effectively absorb and utilize scientific knowledge. Our research has been focused on evaluating the proposed method, and the results have been quite promising. The model we've developed has shown a remarkable ability to absorb technical knowledge, including complex concepts like LaTeX equations and chemical reactions. This capability has proven to scale smoothly with the size of the model, demonstrating its potential for future applications. In terms of citation prediction, our model has outperformed both sparse and dense retrieval pipelines. This suggests that language models could provide a valuable new tool for exploring scientific literature and knowledge. Furthermore, our model has excelled in knowledge-intensive question-answering tasks. It can compose a curated knowledge base and perform step-by-step reasoning, showing strong performance over existing methods. This indicates that language models could potentially take on knowledge tasks that are currently human specialisms. In summary, our research has shown that language models have a strong potential to disrupt the traditional store and retrieve paradigm of accessing scientific knowledge. Our research has yielded some key technical results. Firstly, we found that language models exhibit a strong ability to absorb technical knowledge. As the size of the model increases, this absorption capability scales smoothly. This was demonstrated through the model's proficiency in understanding complex LaTeX equations and chemical reactions. Secondly, our model has shown impressive performance in citation prediction. It has outperformed both sparse and dense retrieval pipelines that have been fine-tuned for this task. This suggests that language models could provide a valuable new tool for exploring scientific literature and knowledge in the future. Our model has demonstrated impressive performance in knowledge-intensive question-answering tasks. By utilizing a curated knowledge base, it was able to effectively answer complex queries. Furthermore, the model showed potential in learning tasks such as IUPAC, naming through self-supervision. It was even able to formulate drug discovery tasks in a natural language prompt, showcasing its versatility. The implications of these results are profound. Language models, like ours, have the potential to take on knowledge tasks that are currently specialized human tasks. However, we must also acknowledge the current bottleneck in language model performance: the availability of high-quality, step-by-step datasets. As we continue to improve and refine our models, addressing this bottleneck will be a key focus. Our research has shown that boosting performance is possible by increasing the number and size of datasets that bridge between natural language and natural sequences. This approach allows us to leverage the power of language models to understand and interpret complex data structures. Looking ahead, we see potential in expanding the size of the corpus used. Current constraints could be relaxed, opening the door to a much larger corpus. This could further enhance the model's ability to understand and generate accurate responses, paving the way for more advanced applications of language models. Our research has delved into the potential of language models, exploring their capacity to absorb and utilize scientific knowledge. We've disrupted the traditional store and retrieve paradigm, demonstrating that language models can strongly absorb technical knowledge, and this capability scales smoothly with model size. Take a look at the figure on the screen. It illustrates the training process of our language model, showing how validation loss decreases with training for all model sizes. It also indicates the point of overfitting, which is crucial for understanding the model's performance and scalability. Our language model outperformed tuned sparse and dense retrieval pipelines in citation prediction. It also excelled in knowledge-intensive question-answering tasks. We've shown its potential in learning tasks like IUPAC, naming through self-supervision, and formulating drug discovery tasks in a natural language prompt. This opens up exciting new avenues for the application of language models in scientific research.